All right, so we're going to look at fracture. Um, and we're talking about stress. If stress is too great, obviously there'll be a fracture or something will happen to the object. Um, the ultimate strengths of materials under tensile stress, compressional stress, and shear stress have been measured. So we have that information usually in charts. There's probably some in the textbook, but you can find them online. When designing a structure, it's a good idea to keep stress less than 1/3 to 1/10 of the ultimate strength. So you want to really limit the stress that you're going to put on your materials. Like for example, a horizontal beam, whether it be in a roof or on a bridge or whatever, will be under two types of stress: tensile stress because it's being stretched, and then compressive stress because it's being pushed down due to its own weight. So those are things you have to consider as an engineer. So here's an example. You got a walkway, you get one above the other. The supports were meant to be 14 meters long. As they installed them, they decided that the long supports, this 14-meter, were too difficult to install. The walkways were installed this way instead, where you had a partial one and then you had another partial one. So two less than 7 foot, or maybe just a tad less than 7 foot because of that gap way instead. Not a major change until you look at the bolts. Okay, so you look at here, you got the net force on the pin here is just mg going upwards. So the vertical rod being the force on that is just the mass of the actual platform. Now, when modified, the net force on both pins together is still mg, but the top pin has more force, 2 mg on it, enough to cause it to fail, which it did. So making that adjustment ended up causing it to fail. And those are things we're going to look at kind of in the problems that would be I don't know if you'll see this on an AP test, but it's something to think about, especially if you're an engineer. If you're going to be a mechanical engineer, you're going to build. This is minimal amount of physics that you will do. So let's go back talking about the piano wire from last video. The steel piano wire we discussed then was 1.6 meters long with a diameter of 0.2 centimeters. Approximately what tension force would break it? Do it now.
Okay, so we got the same piano wire. Here's the work that I did for that. The area is what we're going to keep because we need that. The big thing is we want to find the tensile strength. So, so it's force divided by area. So tensile strength is going to be the force divided by area. So we want to see what force is going to actually make this thing break. Obviously, we didn't break it with our 981 newtons of force. So let's see what that force would be. Now, tensile strength, again, is going to be force over area. We got the area. We want to solve for force. So what's the tensile strength of steel? So there's a chart for that. It's called the ultimate strengths of materials. And the tensile strength of steel is 500 times 10 to the 6th. So I go 500 times 10 to the 6th is equal to force over 3.14 times 10 to the negative 6. So a lot of this type of work is finding numbers. I mean, finding constants and chugging, plugging and chugging. 3.14 e negative 6. So the force would be 1,570 newtons. And once we reach that amount of force, that wire would snap.
So here's the example I was just talking about. Two walkways, one above the other, were suspended from vertical rods attached to the ceiling of a high hotel lobby. The original design called for single rods 14 meters long, but when such rods proved to be hard to install, it was decided to replace each rod with two shorter ones. Determine the net force exerted by the rods on the supporting pin, A, for each design. Assume each vertical rod supports a mass M of the bridge. There's the drawings. Do it now.
Okay, so when we look at the two situations here, and I'll let you look at the board while I talk. So the single rod exerts an upward force equal to mg. All right, so that's this right here. So the single beam does that. Because the pin is in equilibrium, and the other force that bounces out is a downward force exerted by the upper bridge. So there is a shear stress on the pin because the rod pulls up on one side of the pin and the bridge pulls down. Now, when you have two shorter rods, all right, in which the only connections at the upper bridge are shown, the lower rod exerts a force of mg down, but then the upper rod has to support, it's 2 mg going up. So when you substitute two shorter rods, the stress on pin A is doubled because pin A is now supporting two different things, okay? So what perhaps seemed like a very simple substitution to save a little bit of money, in fact, caused a tragic collapse. So by doing that, a single pin actually was less stress than by putting two double pins or two pins into it, which maybe you'd expect, maybe you wouldn't. But that just put way too much stress on this pin because it had to hold up everything below it and everything above it, and that would